Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of how to think about complex numbers acting on the complex plane via multiplication. That is, we saw they acted on the complex plane by rotating the complex plane by whatever the argument of that complex number was, and then stretching the complex plane by a factor of the modulus of that complex number. And we could extend that idea then to talk about how one complex number acts on another via multiplication. In turn, we can say what it means to talk about the multiplication of two complex numbers. And we saw how to do that is we take one of those complex numbers, we rotate it by the argument of the other one, and then stretch that new vector by the modulus of the original complex number. So that's how we multiply two complex numbers. And in this video, we want to look at how to think about how to take a complex number and act it on the complex plane via division. And the way in which we can think about that is we can think, well, division is effectively the opposite of multiplication. So however a complex number acts on the complex plane via multiplication, the way in which it acts on the plane via division must be the opposite of the way that it acts via multiplication. And that's how we're going to construct it and how we're going to visualize it. So let's go to our first animation. And as usual, we're going to bring up the complex plane. Our title here we've got as Complex Division and Conjugation. We will also introduce this idea of conjugation in just a moment. But first of all, we're going to talk about what it means to do the division of two complex numbers and how we can think about a complex number acting on the whole complex plane via division. So let's take two complex numbers on our complex plane. We've got a number here that we represent by this red arrow, which is a complex number z, and another one represented by our green arrow, which is the complex number w. So let's first think about how w acts on z via multiplication. Well, recall that w acts on z via multiplication in the way that it rotates this red vector by the argument of w, and then it stretches that red vector by the modulus of w. So if we were to think about how w acts on z via division, it's going to do the opposite of those operations. So that is, when we first rotated it by the argument of w, the first thing that we're going to do when we're acting on z via division is we're going to rotate it by minus the argument of w. That is, we're going to rotate it clockwise by whatever the argument of z was. Sorry, argument of w was. And then what we would have normally done now is when we act it via multiplication, we would have stretched it by the modulus of w. But because we're acting via division, and we're thinking of division as the opposite of multiplication, that would mean that we shrink it by a factor of the modulus of w. In other words, we scale it down by a factor of 1 over the modulus of w. And that gives us this corresponding vector, and whatever the kind of tip of that vector is pointing to is the point in the complex plane we think of as z divided by w. In other words, we're thinking of w acting on z via division in the kind of opposite way to how it acts via multiplication, because we think of kind of division and multiplication as mirror images of each other. But importantly here, so recall when we talked about multiplication, that if we had w acting on z via multiplication and z acting on w via multiplication, those things were the same. In other words, z times w is equal to w times z. But if we now look at how z acts on w via division, well, let's again think how it acts via multiplication and reverse that. Well, it acts via multiplication by rotating w by the argument of z, and then it would stretch that green vector by the modulus of z. So the first operation is we rotate by the argument of z. So if we divide by z, then we would rotate it by minus the argument of z. In other words, we rotate it clockwise by the argument of z. So that gives us this corresponding green vector here. And then we would have stretched it by the modulus of z, but in this time we're going to shrink it by the modulus of z, or scale it by 1 over times the modulus of z. So that gives us this kind of tiny green vector here that you can hopefully still see. And the point that this vector points to is what we think of as w divided by z. That is z acting on w via division. Okay, so the next thing to think about is how does z take this complex number here? In particular, we've got this complex number that corresponds to 2 plus 2i. So it has argument pi over 4 and its modulus is 2 root 2. How would that act on the entire complex plane via division? Well, it would act on the entire complex plane via multiplication by rotating the complex plane by pi over 4 radians anti-clockwise, and then stretching the complex plane by a factor of its modulus, in other words, 2 root 2. So doing division on the complex plane, acting on the complex plane via division, would do the opposite of those operations. That is, we first rotate the entire plane by 45 degrees or pi over 4 radians clockwise about the origin. And then instead of scaling it up now by a factor of 2 root 2, we shrink everything down by a factor of 2 root 2. In other words, we get this kind of corresponding transformed complex plane. So that's how z, this point, acts on the entire complex plane via division. And similarly, we can realise that we could do those operations the other way around and we get the exact same thing. That is, we could think of it instead first scaling everything down and then rotating by 45 degrees. So we see that we get the exact same result regardless of the way that we thought about z acting on the complex plane via division. We could either first rotate and then scale down, or we could scale down and then rotate. Those were exactly the same. But let's see now that we talked about how we constructed division as the inverse operation of multiplication. So that is, if we act on the complex plane via multiplication first, and then act on it via division, that should be the same as doing kind of nothing. In other words, multiplying by 1. And what we're trying to think of here is that we're saying z divided by z equals 1. So let's see if that is actually the case by thinking about it on transformation to the complex plane. If we transform the complex plane via multiplication of z, that rotates it anticlockwise by 45 degrees and then scales it up by a factor of 2. And now we want to take this new transformed complex plane and act it via a division of z. That is, we rotate it 45 degrees clockwise and then scale it down by a factor of 2 root 2, which gives us exactly what we had at the beginning. In other words, first doing a multiplication by z and then dividing by z is the same as timesing by 1. Which is the standard result that we expect. And you can see as well, if we did the other operation, if we first divided by z and then multiplied by z, that's the same as multiplying by 1. So, given all this, we can write down a reasonable algebraic definition of complex division. And the first one we're going to write down, much like before, is going to use the polar form, because that's much easier to write and kind of ties in with this geometric picture we've constructed. And that is, if we take z, and the modulus of z to equal r1, the argument of z to equal theta1, the modulus of w to equal r2, and the argument of w to equal theta2. Then the complex division, in other words, the division of z over w, or z divided by w, is given by r1 divided by r2, cosine of theta1 minus theta2 plus I sine theta1 minus theta2. And we saw that in this geometric picture here, right? We saw that if we thought of multiplication as adding together the arguments, then the opposite of that, if division is to be the opposite of multiplication, we want to subtract the arguments, which is why we have theta1 minus theta2. We think of subtraction as the inverse of addition, much like division is the inverse to multiplication. And we've got here that we have r1 divided by r2, because previously when we multiply, we have r1 times r2, and on the real numbers, the opposite of multiplication is the division of real numbers. So that's why we've constructed that. So that exactly corresponds to what we've just talked about a minute ago in this geometric picture. Now, the next thing to do, you might think, is before we talked about kind of how to multiply complex numbers in polar form, and then we talked about how to multiply them in Cartesian form. But in order to talk about kind of how complex numbers divide in Cartesian form, we first need to introduce a new concept known as the complex conjugate. Now, this sounds rather fancy, but is nothing more than simply the operation of reflecting complex numbers in the real axis. That is, given this complex number here, for example, z, which we've taken here to be 2 plus 2i, if we reflect it in the real axis, that is otherwise known as the complex conjugate of z. So that is, complex conjugation just simply reflects the entire complex plane in the real axis. And this point here, where z was the previous red dot has now been reflected, this new red dot here is what we write down as z bar, or the complex conjugate of z. And we can write that algebraically in a very simple way, just using the Cartesian form. That if z there was, for example, a plus ib, then the complex conjugate of z is simply a minus ib. But we really see all we're doing here is we're reflecting the complex numbers in the real axis, and whatever that resulting complex number is what we call the complex conjugate. Okay, so I claimed that this was going to be useful for defining a Cartesian version of complex division. And in order to do that, it's kind of first useful to look at some properties of the complex conjugate. So let's bring back up z and kind of draw in two red arrows now, or two red vectors corresponding to z and z bar, the complex conjugate of z. Well, what we notice is if we look at the argument of z, which in this case is pi over 4, that's identical, well, to the argument of z bar, but simply with a minus sign. So this, we realise, is actually going to hold in general that given any complex number, if its argument is theta, then the argument of the complex conjugate would be minus theta. Right? And that just follows because of the way we construct the complex conjugate. It simply reflects everything in the real axis. Therefore, the way in which we define these angles theta by constructing these right angle triangles doesn't change the geometry of those triangles anywhere. The height of the triangle is still going to be the same, and the width of that triangle would still be the same. So the angle is still going to be the same. The only difference is we're flipping everything from the top half of the plane to the bottom half, meaning all the positive arguments become negative arguments, and all the negative arguments become positive arguments. So that makes sense geometrically. And we then ask ourselves the questions, what would happen if we have z times z bar? Well, because the argument of z is equal to minus the argument of z bar, we see that in this situation, if we do z times z bar, that's going to give us a total always of argument of 0. In other words, if we do a complex number and multiply it by its complex conjugate, it's always going to give a positive real number, because if something has argument 0, that means that it lies on the positive real axis. It's going to be in the positive real numbers. So if we take z times z bar, we know it's going to be on the positive reals. And we can just think about, we know how z acts on z bar by multiplication, and equally z bar acting on z by multiplication. That is, we just rotate, for example, z down by 45 degrees onto the real axis, and then stretch it by the modulus of z. But we also notice that the modulus of z is going to be identical again to the modulus of z bar, and that follows again just from this geometric picture of reflecting complex numbers in the real axis. We're not changing the geometry of these triangles in any way, or the distance they are away from the origin, so the modulus of z is the same as the modulus of z bar. In other words, what we realise here is that the modulus of z is equal to the square root of z times z bar. Because if we've got z times z bar, that's going to take us down to the real axis, and that's going to equal exactly the modulus of z squared. So if we take the square root, or the principal square root, we see that the modulus of z is in fact equal to the square root of z times z bar. And this is going to be a particularly useful identity to also use throughout all of complex analysis to kind of rearrange the formulas and utilize in many different ways. We'll also utilize it in a minute to talk about how to write complex division in Cartesian form. So we've got some information now about the complex conjugate and how it relates to these things. So let's, like before, we're going to remove all the points, and we're just going to look at, say, the real and imaginary axis. So these grid lines now don't necessarily correspond to one unit along or so forth. We're going to take them as general. In fact, for the programmatic purposes, these do actually correspond to kind of 1 unit along and 2 unit along and so on, but you can think of these as kind of a general coordinates on the complex plane. So like before, we're going to take 2 complex numbers. We're going to take z and w, and we're going to write down the kind of arrows corresponding to those, the vectors corresponding to those. And in this case, we take w is equal to c plus di, and z we're just going to leave open. And much like before, we kind of constructed z times, or w times z. We thought of w acting on z, which is the same as z times w, but it didn't really matter. And then we constructed whatever that vector was by kind of rotating it and stretching it, and then realizing that we could also build that vector by just taking multiples of z and iz by multiplying it by either kind of the imaginary or real parts of w. And in this situation, we want to kind of figure out if there's a similar way in which we can derive the division of complex numbers by simply using the Cartesian form. So the way in which we're going to start doing this is we're first going to look at what w times z is. So we know how to do that. That is, we take the point, this red vector z, we rotate it by the argument of w, which in this case is negative, so we rotate it clockwise, and then we stretch it by the modulus of w. In other words, that gives us this point here, which we write as w times z. We describe it by this yellow dot, and we're going to take this yellow vector, which is w times z. Now, we know if we can figure out how multiplication is on one complex number, in general, how we constructed it then is it acted in the same way on all complex numbers and the entire complex plane. That is, we saw that if it acted on one complex number by rotating by its argument and then stretching by the modulus, we said then, or we extended it to the entire complex plane by doing the exact same thing. So what we're going to do here now is we're going to kind of use that idea, and we're going to say, is there a way that I can get from wz to z via only using multiplications of w, its complex conjugate, and its modulus? And if we can do that, because we can write multiplications in this Cartesian form, then in turn we will have written division in a Cartesian form. Because the action of taking wz to z, this yellow arrow to the red arrow, is in other words acting wz by w via division. So in other words, we're doing wz divided by w. So we want to find what the transformation is of taking this yellow arrow to this red arrow, only using multiplications of w, w bar, and its modulus. Okay, and if we can do that, then we can extend it to the whole complex plane, because we know how it acts, or at least w in this situation, or how a complex number acts on one complex number via division, it must act on all complex numbers in the same way via division. So the first thing we did, or the first thing we're going to do, is we want to do kind of the reverse operation of the last thing that we did to get to wz. So the last thing we get to wz was we stretch that vector by the modulus of w. So let's first scale that yellow vector down by the modulus of w. In other words, we times it by 1 over mod w. So that takes us to this point here. And the next thing we'd like to do is we'd like to simply rotate that yellow vector now by minus the argument of w, because initially z was rotated to that yellow vector by rotating it by the argument of w. So taking it the other way, we want to multiply it by a vector that has minus the argument of w. Well, we've just realized that if we take the complex conjugate of a complex number, that gives us the corresponding argument of that complex conjugate is minus the argument of the initial one. So what happens if we take this yellow vector and we multiply it by the complex conjugate of w? Well, that's going to orientate that vector. It's going to take it so it's now lying over the red vector, but it's also going to stretch it, right, by a scale factor of the modulus of w. Or the modulus of the complex conjugate of w, but we've already seen that the modulus of the complex conjugate of w is equal to the modulus of w. So we're kind of almost there. We've kind of overstretched the mark, right? We've got now the orientation is correct. It's the yellow arrow is lying over the red arrow, but we want to bring it back down now to the point, so this kind of yellow arrow lies over the red arrow, so it corresponds to the point z. And the way in which we're going to do that is we want to scale it down by that factor that we've overstretched by. Well, we overstretched by the modulus of w. So in other words, we want to scale it down by the modulus of w. In other words, we multiply by 1 over the modulus of w. That is, we see that we can think of a z as equal to that wz, that point that we had, multiplied by the complex conjugate of w divided by the modulus of w squared. Now, what we've realized here is we can otherwise think of wz, that if w acts on wz via division, which is going to equal z, in the same way as multiplying wz by w bar over modulus of w squared. And because we know how to write the multiplication in Cartesian form, that will allow us to write the division in Cartesian form. So in other words, we can realize that acting on the complex plane here via w, or acting on the complex plane by dividing by w, is the same as multiplying the whole complex plane by w bar and then scaling it down by a factor of the modulus of w squared. So let's see that in action here. So our claim now is that we've got our kind of complex number z, and we said that we want to think of division and multiplication as the opposite of each other. So let's first act on the complex plane via z and via multiplication. So in other words, we rotate everything by 45 degrees anti-clockwise, and we stretch all by a scale factor of 2 root 2. Great. Now, if we act it via division, that should take us back to where we start. But we're going to claim that acting via division, in the way that we talked about before, is the same as multiplying by the complex conjugate of z and then scaling it down by a factor of the modulus of z squared. So what would happen if we multiplied the complex plane here now by the complex conjugate of z? Well, that would correspond to initially rotating it clockwise by pi over 4, because the complex conjugate of z would have argument minus that of z. So in other words, that takes us a rotation clockwise by 45 degrees. And then multiplying by the complex conjugate of z is now going to stretch it by the modulus of z. So we're going to kind of stretch it as well by that scale factor of the modulus of z. So in other words, we took that previous complex plane and we've multiplied it by the complex conjugate of z. But now our claim is that we then scale it down by a factor of the modulus of z squared. So if we scale everything down by a factor of 2 root 2 all squared, that brings us back to this point. In other words, we saw that we can think of division as the same as multiplying by the complex conjugate and dividing by the modulus squared. So that allows us now, kind of writing all our things in as in Cartesian form, if we expand everything out, in other words, what you can see here is if you write in z equals a plus ib and w equals c plus a di, we can expand all that expression just using the usual multiplication rules for Cartesian forms of complex numbers, and you will get exactly this expression here. In other words, z divided by w, we said was the same as z times w bar divided by the modulus of w squared. That's what we saw here. And if you put in all those values of z equals a plus bi and w is equal to c plus di, plug it all into that, you would get exactly this expression here, which tells you how to divide two complex numbers in this Cartesian form. So that's where we're going to conclude the video. And in the next video, we're going to talk about a kind of general theorem about raising complex numbers to powers of integers, and this is otherwise known as Denoise Theorem. And then we're going to move on to talking about kind of probably one of the most famous formulas within mathematics or within complex analysis, known as Euler's formula. So once again, I remind you to read the notes after watching this video, because the notes complement the video. In here, we're talking a lot about the geometry. In the notes, you can look up more of the algebra and some examples in there, and as well to attempt any problems relating to the topics that were covered in this video. So thanks very much for watching, and I'll see you in the next one.